Everyone. Good afternoon, everyone. Thanks for the opportunities for us to present our recent studies on the structural integrity of our 3D printed prosthetic socket. The presentation today will include some preliminary results of our experiment study for the lower limb prosthetic sockets for the pediatric applications. And the current challenge for the prosthetic socket manufacturing industry and in general is that the current manufacturing methods requires a very labor-intensive means of work, and it takes a lot of times, which needs to generate a positive mold from the user, and then from the positive mold, the prosthesis usually needs to cast a negative mold, then based on trial and errors and artisanal labor-intensive means to produce several sockets in order to define the final shapes of the prosthetic sockets, which is costly and time-intensive. The alternative approach recently, I think, in hot potato areas, is that people are starting to use digital methods or fully digitizations of the manufacturing principles. Generally starting with 3D scannings of the anatomical limbs, and then through various different ways of optimization, either through computer simulation driven or through manufacturing optimization methods to develop and manufacturing the prosthetic socket. Today, the topic I would like to present is mainly focusing on the testing and certifications of the prosthetic socket, where once the socket designs are stationed, and how do we test and prove the prosthetic socket, and what we can learn from improving the manufacturing methods of the prosthetic socket. The existing limitations that we see from the literature before we started our studying was that the current prosthetic sockets that are available in the literatures or through the industry are either bulky, which generally speaking that the thickness of a socket can range from 10 to 20 millimeters, and the weight is very heavy for the user, typically range from 500 plus grams. And usually the manufacturing process requires specialized printers or materials that is quite limited to the wider general populations in terms of usage. And therefore the load bearing capacities from existing study from the literature that we can see here, that is not acceptable. So on the average of the load bearing capacity, and as a result, the cost of replacement and the time and frequency for the replacement is intense due to the manufacturing method that it adopted. So our design approach are the following. These are the design objectives for our study, which we would like to design a fully digital and conformed geometry of the prosthetic socket. And we want to use widely accessible printers as well as materials for general populations for wider adoptions of this technique. And we would like to limit our weight of the prosthetic socket, which will be below 500 grams, which is the threshold of the existing socket that we saw in the literature. And we would like also to optimize load bearing capacities, and the tests should satisfy the existing ISO standards of the prosthetic socket testing, as well as reducing manufacturing times and costs. Okay, the socket testing protocols that we follow was according to the ISO standard, as we saw here, and we use the maximum load bearing capacities of condition 1, which is at the maximum of the weight acceptance stage, which is the heel strike stage of the loading cases. And the maximum load was scaled down according to P5 loading condition, which would be equivalent to a 98 percentiles of a 14-year-old male in UK average weight, which is around, oh, sorry for my, I think my presentation flows on. which is roughly equivalent to 74 kilograms of the body weight. We used silicon phantoms to represent the likelihood of the soft tissue during the deformation, and the testing setup can be seen on the right-hand side of these slides. And in terms of our study designs, we have 3 testing groups. The first testing groups is based on the original socket design that we taken from, which were provided to us from bioprosthetists with a flat-based design. And the modified socket design was the second group, which we rounded up the bottom of the socket base. And the third group is basically our custom print path that we use our in-house code to generalize the printing path, and that can recreate the same round-based socket design, but using a fully customized slicing software, which then in the future can produce a gradients of wall thickness and varying wall thickness according to our needs. Okay, so some of the preliminary results of our current study for the group 1 that you can see here, that based on our testing results, what we can see is that the crack path generally initiates from the posterior end of the socket, where the maximum load bearing capacity, where the maximum load points were applied during the heel strike stage. And there were prevalence of the interlaminar failures, where we can see for majority of those sockets, failure happens at the interlaminar, which is the lamination between the adjacent layers of the material. I do apologize for the auto enrollment of the slides. And the base of the socket generally saw as a detachment, which significantly reduced the load bearing capacity of the original design of the prosthetic socket shape. And the second groups, some initial results that we see here is that it's a clear observation that the testing, the failure modes shifted from predominant interlaminar shear failures from both interlaminars and intralaminar failures. And the failure initiates, instead of the bottom posterior side initiated, it's starting from the top anterior side and propagates from as an interlaminar failure through the lower posterior sides of the socket. And the third groups of our testing results, as you can see here, shows that on the top right corner here, the figure, we see the black image here, the black socket, indicating the traditional group 2 testing, which we saw the interlaminar shears, delaminations, while in our custom print path, we saw a much ductile deformations and ductile failures happening as opposed to brittle fracture that happens to the previous 2 groups. In addition, for this optimized design, we want to also test that this transition from brittle to ductile failure was not due to the structure properties or structure profiles of the socket. Therefore, we did further studies on short beam shear tests to testing whether our custom print pass would improve the material performance rather than the structural performance of the socket. As you can see from the lower right corner here, that the short beam shear test results indicating that as the red area indicate is the custom print pass, as opposed to the standard slicing software, which indicating as a gray or white background area, and that we show a strong improvement in terms of the material performance rather than the structural performance. Finally, I would like to share some of our preliminary testing results, as the data was still in compiling stage. This is obviously not shared in our 3 groups, but all the testings were combined into different colors without the group representation. But what you can see here is that the red and the blue sockets were the testing socket that from the standard geometry, and the blue or the ruby colored was the custom print pass socket, which the design results. Sorry, I do apologize for the sliding of my slide. This is our group 3 testing result, which indicating that the maximum load bearing capacity reached beyond 10,000 newtons capacity. Some preliminary results again from our optical microscopies and SEM images of interlaminar sheared testing sockets. We can see a widely delaminations of interlaminar shears, which we hypothesized that the interlaminar shears was also partly due to the stress risers from these porosities that we observe between the interlaminar gaps of the prosthetic socket. Just to conclude, our current preliminary study was that our fully digital design for additive manufacturing workflows can produce a highly customizable and a prosthetic socket which can improve the maximum load bearing capacities. And the approach usually take on wider printers that is available for us, which is low cost 3D printers. And we generally use a single PLA, which is mostly accessible printer FDM-based printer materials for wider populations. And in terms of the manufacturing and the performance of our printer, our 3D printed prosthetic socket, we can see that we can have a maximum 90% of time reduction in terms of printing times using our custom print pass compared to the standard printing pass design. And we have a very high strength to weight ratios of 72 grams newtons per gram as opposed to the standard printing pass of 35 newtons per gram. Our newly optimized load bearing capacity range from 5,800 newtons to about 10,000 newtons, which is approximately eight times of the body weight, which we believe that would fully satisfy the load bearing capacities of the ISO standard of prosthetic sockets. And our low cost manufacturing estimate of the manufacturing cost is just around 30 to 50 pounds for the material that we use. Obviously, these should be fully factored into some other cost of labors and usage of the print time. But we generally believe that this is a quite good approach that we would like to take forward for the future as well. Okay, so I think that's the end of our presentation and study. So thank you so much for your time. Happy to take any questions.